All right. So hi, I'm Bala. I'm Positron Dynamics. I have a few slides here today, so I'm going to more like freewheel a little bit. And actually, I just did a talk yesterday, another event where I had a time limit of 7 minutes. So this is lavish time to talk about this topic. Actually, someone earlier on brought up the notion of how CubeSats, you can pack a lot of complexity into CubeSats. And so this would be an example of where we're trying to really push that limit. Kind of to tie it to the lunar, so I kind of got to this event because Sean Casey asked me, and he was like, hey, do you want to give a talk at this Lunar Cubes event, which I hadn't really heard of before. So it was like, oh, great, I'm in town, so sure. And I looked at your agenda, and it seemed like some really interesting talks in the last couple of days. So to kind of give the background of where we came from, basically my two co-founders, Josh Mahacek and Ryan Weed, they're positron physicists. I'm an engineer. We happen to be working on a Google Lunar X Prize team together, along with Sean Casey, actually. And over the course, that project kind of came to a close, and we went our separate ways. But then this opportunity came about. I used to be active on Twitter at the time, and I saw Peter Thiel, who's one of the co-founders of PayPal and runs a number of venture firms and investment companies. So he had done this talk at Stanford where he said he's going to start this initiative called Breakout Labs, which I have a pretty freebie from the event I was at. Anyway, so this was a couple of years ago, and I was like, hey guys, we should totally propose this concept. So I haven't yet told you what we're working on, and that is positron-based propulsion. So essentially, we founded this company around the premise of, antimatter has been talked about as a, for decades, almost since the 40s or 30s, like as a potential, something you use for propulsion. It would be, how can you tap into this immense energy density, like 90 megajoules per microgram? How do you convert that to, how do you get from there to propulsion, or, how do you use that energy? And in order to do anything relevant with antimatter, you need to be able to produce enough of it. And that's really the core, the idea around which we started our company. Ryan and Josh happen to be working on positron physics, and positrons are the more abundant, easily available form of antimatter. Positrons are the antiparticle of the electron, and when they meet an electron, they annihilate and produce gamma rays. And so then we started throwing around the idea: how crazy can we get with this? Can we actually create propulsion? Using that energy from the annihilation to catalyze a reaction. And so let's see, here's the clicker. Where do? Oh, okay. Okay.
Oh, speed, we don't have the focus.
Maybe this will work. This.
Let's try this.
Yeah. There you go.
All right.
Okay. Yeah. So. I've already mentioned a couple of members of the team. Ryan was here for a few minutes earlier, but he had to catch a plane, so he left. So Ryan and Josh had a background in positron physics and investigating materials and interactions of positrons with materials. Now, positrons is commonly available source is a radioactive isotope produces a distribution of energies of positrons, and then you need to cool them down. In order to have them interact with matter in useful ways, you need to cool them down because you have a lot of high energy positrons that just kind of go through materials. So you need to cool them down or moderate the positrons, and that, and then we created some IP around this from the work Ryan and Josh did as part of their PhD research, and out of that spun out this company. So we got our initial funding, seed funding, from Breakout Labs. This is actually a highly abbreviated slide deck. I should have put the longer deck in where we had a picture of our lab in Livermore, California, where we have our ultra-high vacuum setup, and we're trying to optimize how moderation happens, and get to an order of magnitude improvement in slowing down positrons. And that's really what we've been working on the last year. You may have noticed the Cornell logo that was on the first slide here, and yeah, actually that's a good transition. Yeah, we also have Mason Peck is our spacecraft collaborator, and we've been working with Cornell on the design of a spacecraft demonstrator that would do an in-space demonstration of once we do some things in the lab. So this slide kind of provides a cartoon of what's going on. You have, you know, most high-performance propulsion concepts that have been proposed over the decades seem to involve like a large nuclear reactor needing to be there in space in order for them to go anywhere. So we're like, you know, how can we squeeze this down to, you know, something that, you know, a propulsion module that would fit in a, you know, maybe a CubeSat, or you know, 1U of a CubeSat, for instance. You know, the concept involves a radioactive sample that's within the permissible realm, and then you take a moderator array, that's our technology we're developing to slow the positrons down, and then you interact that and catalyze reactions to produce thrust. Now, that's really the high-risk portion of this whole venture, is like doing that experiment to figure out, like, you know, can you even produce thrust? Can you catalyze reactions? Can you produce meaningful thrust? And so that's really what we're raising funds right now to work on. Next slide, please. In terms of applications, yeah, I know this is a lunar. I think some of the business stuff may be more useful, and we chat about it after this talk. But in terms of applications, low Earth, really low Earth observation, low Earth orbit observation is one potential application of this sort of propulsion technology, where you have a really high ISP and a thrust that's comparable to a high performance ion thruster. And you know, essentially extending the lifetime of a CubeSat or a small satellite that's dwelling at a really low orbit for from a matter of days to over a year. That would be one close to home application. Eventually, you know, we hope to get to Alpha Centauri, but there are a few steps. Next slide. Yeah, okay, so yeah, what are these steps? So the most immediate, so we're working on the moderation experiments, and from there, the next step that we're progressing to is doing an experiment to show that you can actually catalyze a reaction that would be suitable to produce charged particles that you can then guide with a magnetic nozzle to produce thrust. From there, since all of this is, we're designed this whole thing around being as compact as possible, because one of the applications we're also going after is non-destructive testing, using like a portable non-destructive testing unit that takes advantage of this moderation process of positrons. So we've tried to make this thing as portable and small as possible, and so we think it can easily translate to a CubeSat concept. Granted, there are lots of design challenges there. What do you do with the radioactive source? How do you make sure you don't fry your own electronics, and so on? But then you know, I think there are a few demonstration flights you could do that would pave the way to doing something really exciting, like if this works. So with that, I'll conclude my talk. Here's a little model our intern built, if you want to see. It kind of shows the different pieces of the propulsion system. But yeah, I'll take questions.
So yeah, so your startup is a novel one, but it's also something that comes up especially in space and science startups. So thanks for being here. Thanks for your presentation. So the way I remember it from this and the previous presentation, I saw your kind of day job is to work on the moderator at Lawrence Livermore.
Yeah, well, not at Lawrence Livermore, but
yeah.
The facility. We have our own
Your own
rented
facility,
space nearby.
But somebody's paying you to do that, right? That's
well, so we got funded by breakout labs. That kind of allowed us to set up the lab and do the initial experiments.
Okay,
so,
yeah.
so that was a decent amount of funding.
Mm-hmm.
And then more recently, we just got into the new class of Alchemist Accelerator, which is backed by Draper Fisher Jurvetson and Khosla Ventures.
Mm-hmm.
And so yeah, that'll be interesting.
Mm-hmm. Okay, cool. So you are then a pure startup, and then that's the interesting thing is you're trying to fund fundamental research, which could be a while before it turns into anything that looks like a product.
Yeah, well, yeah. In a sense, we're kind of challenging the VCs and those types. Like, if you really want to make non-incremental big changes,
Mm-hmm.
and given that nobody's willing to fund fundamental research anymore,
Yeah.
and you can't rely on the government agencies to do that all
Mm-hmm.
the time. For a high-risk project like this, $2 million is a reasonable investment.
Yeah, excellent. Thank you for that. Yes, we have some other people like the Thrust people are in the similar thing. They've got to do quite a bit of research before they get going. Bill?
Yeah, just a quick question. Is your concept that the emission source and moderator collection is part of the onboard system?
So yeah, to be clear, we don't store the positrons before. So it's like in situ. Like you have a radioactive source, you have a moderator. You can turn it on and off based on because we use electric and magnetic fields in our concept. So yeah, there's the moderator structure, and then so the initial iteration is like an in situ product. You have radioactive source, you cool down the positrons, they impinge on something, magic happens, which is the magic we're trying to come up with.
Have you ruled out the onboard storage with magnetic bonds?
No, we haven't. We haven't. I mean, that would be once you produce enough positrons, then you can begin doing interesting things like that. There's also compact linear accelerators that people are building now. So then things start to get really interesting.
So what kind of power, Pamela Clark, lecture engineering, what kind of power requirements would you have for such a system?
I think did we have an estimate on the previous slide here? But it'd be within the realm of, so we're hoping to make it such that, okay, we don't actually, but yeah, it'd be in the realm of, not kilowatts of power. It would be
so hundreds of watts?
Hundreds of watts would be
It's a lot for a CubeSat.
Yeah, it's a lot for a CubeSat. Though the interesting thing is if this fusion concept works out, you'd be able to, because the heat you produce, you'll be able to, from the neutrons, you would be able to salvage some of that to actually power the system.
And you got a thermal thing to deal with.
Yeah, we have it's a challenging problem. And the interesting thing is, like, if you're really going after an interstellar mission where you're like basically radiate, so then it's nice to have a heat source, your little fireplace. So.
Okay, Adrian CubeCam. So I'm understanding correctly, you have radioactive produced antimatter in the CubeSat itself, right?
What was that?
Do I understand correctly that you have radioactive produced antimatter in the CubeSat itself?
So the antimatter production is from decay of nuclear from a radioactive source.
Right, but that happens in the CubeSat.
It happens
right?
in the CubeSat.
Okay, you're aware that the main problem with nuclear propulsion, and that would apply to this too, is political, not technical?
Yeah, absolutely.
How are you intending to overcome the political hurdle?
So the activity of the source we're talking about using for this concept is comparable to what Curiosity or like some of the radioisotopes that are used on some common on NASA missions would be. So it is within the permissible realm. There will be legal challenges, but I don't think that should be a barrier to progress.
Shouldn't be. It probably will be, but shouldn't be. Yeah.
Bonnie, behind you.
Yeah, I'm just trying to convince myself you can get these delta V's. So I think it's in the rocket equation. It's going to come down to the exit velocity of the positrons.
No, it's not. So yeah, that's the point. It's not the positrons themselves, right? So there could be future concepts where you can do like direct annihilation stuff, but what we're talking about is catalyzing a fusion reaction, in the ideal case. So you have a deuterium target, and you catalyze a fusion reaction. But so the thing about the cold positrons is that they will go and seek out the defects where dense deuterium resides in a lattice that you've deposited deuterium in.
But whatever that process is, it's going to have to release the energy in a direction and not other directions for this to work. So how does that happen?
So from the catalyzed fusion process, then you get the particles that come out at fractions of the speed of light. 2.2% speed of light, for instance. So they're significantly fast particles. So it's basically through an array of permanent magnets and potentially superconducting magnets that we will have, so kind of a Hallbach array kind of situation going on to guide the particles out.
So yeah, thanks. So yeah, the result of charged particles that could be steered by magnetic fields.
Yeah, I'll buy that.
Yeah, okay, good. Thanks. Well, thank you very much. We're going to move on and pick this up again.